This is Dr. Anthony Revis, and this is SVSU General Chemistry 111, Chapter 6, Lecture 2. That's Lecture 2 of Chapter 6. Electronic Structures and Periodic Properties. In this chapter, we will look at electromagnetic energy. We will look at the Bohr model and theories related to it. We will also look at development of quantum theory. We will look at electronic structures of atoms, and specifically we will learn about electronic configuration. We'll also look at periodic variations in elements and properties based upon the periodic table. These topics will be covered, however, they might not be covered in this order. In this lecture, we will focus primarily on being able to write electron configuration and being able to draw electron orbital diagrams. So in order to do that, let's start with a review about quantum mechanics, and more specifically about quantum numbers. Quantum mechanics is an atomic concept that recognizes four quantum numbers. But these four quantum numbers are actually written as alphabets. Okay, so they're not exactly written as numbers. And in fact, perhaps for mathematical purposes, you might think of these as quantum variables. Okay, but they are quantum numbers, or they are derived from quantum numbers and from quantum mechanics. But we report them and we talk about them as these four alphabets that look like mathematical variables, or look more like quantum definitions. So just be aware of that. Okay? So there's N, which is a principal quantum number. This number corresponds to the period. Like you have 7 periods on the periodic table, period 1 through 7, if you will. They're all whole numbers. So you have your period. So whatever that period is, that's your principal quantum number. And then you have L, and that's your orbital type subshell. Okay? And this will make more sense as we start to practice it. So we have a quantum number. That will be 1 through some digits there. They're whole numbers. And then we have L, which is the orbital type subshell. And this deals with the angular momentum and the orbital shape, to be more specific. This is your SPDF orbitals. So you have these different orbitals, and these orbitals have different shapes by which they're recognized. So an S orbital is a sphere, P orbital is dumbbell, D is a double dumbbell, then F gets really complicated with lots of dumbbells around them. Okay? L is the orbital orientation, as in XYZ orientation there. It has to do with what's called the radial nodes. And a radial node has to do with where the electron density is located. Then there's the spin, and spin is the easier one to remember. The MS is either spin up, spin down, plus 1/2, minus 1/2. So these are terms that are factors that you have to memorize or become very familiar with, or learn, or in some way be able to retain in order to look at doing electron configuration and drawing electron orbital diagrams. The spin goes according to what's called Hund's rule, by the way. Hund's rule tells you that it has to be spin up, spin down. Can't have two spins in the same direction. So let's repeat this again. Your quantum numbers or quantum variables are N, L, ML, and MS. Your principal quantum number defines whether you're on the first period, second period, third period, etc. L tells us whether or not it's SPDF. ML tells us whether it's XYZ. And spin tells us that it's 1 up, 1 down, plus and minus. Now, there are ways to mathematically get these, and there is math associated with it. There are some professors who ask you to use this math and prove how you know it. I'm going to show you the math, but in most of my lectures, evidence that you understand the math for me is in showing the results and the answers. However, there are occasionally some homework problems in freshman chemistry where you have to be aware of this math. So you're going to learn both ways. Okay? So when we talk about L is equal to n minus 1. And when L equals 0, we have an s orbital. Okay, that means n1. So we have only s orbital. When we have n2, then we have L1, which is a p orbital. When we have n3, then we have L1, which is a d orbital. When we have a 4, then that's an f orbital. So we go 1 through 4 here. Okay, so be aware of that in terms of being able to define. There are only 4 orbitals that you have to remember: the s, the p, the d, and the f. That's it. Okay. There are 2 L plus 1 orbitals with the same L value, and this creates what's called degenerate energy. In other words, there are levels within the subshells and sublevels that have the same energy. So you'll want to be aware of that. For example, a p orbital has 3 shells. That means there are 3 locations where electrons will populate the orbital, and they all have the same energy. D has 5, and that means there are 5 locations where the electrons can populate having the same energy. And F has 7, and so there are 7 spaces, 7 shells where the electrons can populate that all have the same energy. They are all degenerate energies. Now, since there are 2 electrons per shell per degenerate level, an f orbital will have a total of 14 electrons possible for it. A d orbital with its 5 degenerate shells can accommodate 10 total electrons. That's 2 per shell per degenerate level. One spin up, one spin down, according to Hund's rule. So we can add a total of 10 electrons to a d orbital. And a p orbital can have 6 electrons, and a s orbital can only have 2 electrons. Now, you will get familiar with this as we work through it, but I want to make sure we introduce the concept now. So, quantum numbers have N, L, ML, and MS notations. These notations help us to understand what our principal quantum number is, N, what our orbital shell types are, what the orientation is, and whether it's spin up and spin down. We can define these orbitals by the letter L as 0 for S, 1 for P, 2 for D, 3 for F. Because we have degenerate levels, we have degenerate shells, degenerate places where electrons can fill these orbitals. The S can accommodate 2 electrons because of its 1 area, it's 1 shell. P has 3 degenerate shells, 3 degenerate levels. Degenerate meaning equal, so there's an opportunity for 6 electrons. 5 shells for D, 10 electrons, 7 for F with 14 electrons. Alright? So when we think about the quantum numbers and quantum mechanics with regard to electron configuration and electron orbital diagrams, we want to recall that degenerate energies or degenerate levels mean they're the same. Orbitals that belong to different subshells, however, have different energies. And the other thing we want to recall is that an electron can only spin in one of 2 quantized states: positive, negative, spin up, or spin down. That's it. There are no other options. Therefore, if two electrons are to occupy the exact same shell, one must be spin up, one must be spin down, one must be positive, one must be negative. Those are the only choices. So these are the concepts we will use now in moving forward to develop electron configuration synthesis and electron configuration or electron orbital diagrams. When we look then at the periodic table, it is arranged according to atomic numbers. Each element on the periodic table has a unique atomic number. That unique atomic number is equal to the number of protons in that atom, in that element. Because the elements on the periodic table are neutral, the number of protons also equals the number of electrons. Therefore, for carrying out electron configurations of elements and atoms and drawing electron orbital diagrams, the number of protons will equal the number of electrons, which means that we read the number of electrons possible for that atom, for that element, based upon its atomic number. So, for all practical purposes, the atomic number equals the number of protons when carrying out operations involving electron configuration and electron orbital diagrams. This periodic table shows the arrangement according to the S, P, D, and F orbitals, or what's often referred to as the S block, the D block, the P block, and the F block. When we do electron configurations and electron orbital diagrams, we are essentially populating the periodic table with the electrons for each of the atoms or elements in question. Okay, so if we do an electron configuration for example, carbon, we are essentially populating the S and P orbitals with electrons for carbon. If we do an electron configuration, for example, of chromium, we are then populating the electron configuration diagram and orbital diagram with S, P, and D orbitals. Okay, so essentially we're putting the electrons in those orbitals. All right, and we're going to show you how to do that. So as you work through this, you want to occasionally refer back to the periodic table. Now, we can actually do electronic configuration using only the periodic table, but I'm going to show you how to do it using the standard sentence format and the block diagrams that are used for the orbital diagram method. The electron configuration notation method is the standard method of doing electron configuration. Drawing blocks, lines, or circles for the electron orbital diagram is the standard method for carrying out that operation as well. And by the end of this lecture, you will know how to do both those operations. So let's talk a bit further about atoms and electron configuration. Electrons are crucial to chemical reactions because they are responsible for forming chemical bonds to make compounds. You want to make a compound, you need electrons. You have electrons, you have the potential to make compounds. The periodic table arranges atoms so the elements with the same chemical and physical properties are in the same group because of their electron configuration. In other words, there is similarity between the atoms and elements in a group and its electron configuration. The latter part of the electron configuration for atoms in a group will look almost the same, and they will differ, and that similarity is most pronounced when we talk about the concept of valence electrons. Elements in the same group have similar valence electron configurations. Valence electrons are the electrons that participate in bonding. The electron configuration and its valence electrons describe why elements in the same group have similar chemical reactivity. And that's an important principle to hold on to. And we're going to learn how to write that electron configuration out so that we can observe the electrons involved in the similar chemical reactions. Okay? So atoms in a group have the same number of valence electrons. Valence electrons are the electrons in the outer shell, and that's important to remember. And you will see that when we do the electronic configuration or the electron configuration and the electron orbital diagram. They are responsible for bonding. So, a lot of theory, a lot of principles. Let's start to put it into action. Let's start to do some electron configuration. Electron configuration is used to indicate placement of electrons in an atom. In other words, where do you place the electrons in the atom? Where are they located? Electron configuration allows you to visually see that. You must keep in mind as we work through these problems that electrons equal the atomic number. We always start with the atomic number when we work these problems because the atomic number equals the number of electrons. Even when there is oxidation or reduction, which will change the number of electrons, we always start with the atomic number of the atom element in question. That's always the starting point for problems of this type and for understanding electron configuration. The lowest energy level is written first, then sublevels with increasing energy. You will learn how to do that. The number of electrons in each sublevel is written as a superscript and filled with increasing order, called the Aufbau principle. And that's simply the name of the person who became prominent in discussing this method. Okay? So keep that in mind. It starts with the lowest energy sublevel, and that's written first, and then sublevels with increasing energy are added. Essentially, you're going to write a sentence, and you will hear me use that term. You will hear me say we're going to write an electron configuration sentence. And that sentence will look like the 1s2, 2s2, 2p6, 3s2, etc., etc., etc. You will hear me use the term sentence when I refer to that method. So be aware of that. All right? So when we write electron configuration, it is talking about writing that sentence, that 1s2, 2s2, 2p. Do not make the mistake of writing the 2 as a subscript. It is only a superscript. It is also not written as a coefficient behind it. It must be as a superscript. Some of your professors, me included, will be extremely anal about that. Okay? How you write it and how you denote it carries very specific meaning. Okay? So be aware of that. Now, we're going to use carbon as our example to learn how to do this. Once we learn how to do it with carbon, you will follow the same process for any other atoms, any other elements. So, when we look on the periodic table, we see carbon, and carbon has a 6 above it as a small whole number. That small whole number is the atomic number. That is the key identifying character of any atom, any element. It tells how many protons are in that element. That number is also equal to the number of electrons. So carbon with 6 has 6 electrons because its atomic number is 6. On the slides that I show, I will show you the field order. However, this field order matches the periodic table. Because you will always have a periodic table in freshman chemistry, you would be wise to learn how to read this field order from the periodic table. But until we learn that order, in these slides you will see me with the field order listed on many of the slides. So either memorize the field order or learn to read it from the periodic table. So what we're going to do then is take 6 electrons, that is carbon's number of electrons, which equals the atomic number, and we're going to fill the electron configuration with those 6 electrons. There's a very important principle called the Pauli exclusion principle, and it states that each orbital can hold a maximum of 2 electrons. So each box, each line, each circle, you will know what that means soon, can only hold 2 electrons. And they can only be spin up or spin down. So if one arrow is pointing up, the next arrow should point down. So before we fill this carbon atom with its electrons, let's take a look at what we mean by that order of energy. The diagram on the left starts with period 1 at the bottom, and we work through the other periods as we go. And so we will start with a 1s, work through a 2s, we will then go to a 2p, then to 3s, then over to a 3p, 4s, 3d, 4p, 5s, 4d, 5p, and so on, shown on this diagram. This order of filling exactly matches the organization of the periodic table. We show you that order on the bottom of this slide as well. So this is how we read the diagram. The order of the orbital filling starts at the bottom and it works its way toward the top from the lowest energy to higher energy. You either memorize the order or read it from the periodic table. A couple of tips for filling in orbital diagrams and for writing electronic configuration. The S orbital can hold a maximum of 2 electrons, which means it will have one filled shell, one line, one box, one circle, one oval. The P can hold a maximum of 6 electrons, therefore it will have 3 filled shells, 3 filled spaces. D can have a maximum of 10 electrons, therefore it will have 5. And F can fill a maximum of 14, therefore it will have 7. So regardless of how many electrons are available to be used, you can never draw a p orbital without drawing 3 lines, even if you only need the space for 1 electron. Keep that in mind. That is a common mistake. So if you draw a p orbital, it is not 1 line, even though you only have 1 electron to fill it. You must draw all 3 lines, and in that case, with 1 electron, you will have 1 electron in the first one, and the other 2 will be completely empty, but you must show them for it to be a properly drawn p orbital. Likewise, with drawing a properly drawn d orbital must have 5 lines. Regardless of how many electrons populating the d orbital, it must have 5, and an F must have 7 slots available. So if you draw an F orbital, it must have those 7 slots available for filling. Okay? That is critically important to drawing electron orbital diagrams. It is also helpful to know when writing out the electron configuration, which is the sentence format of reporting electrons in an atom. So let's start to do the electron configuration for carbon. So let's write out the electron configuration for carbon using the sentence format. Again, the sentence format is the 1s2, 2s2, 2p6, etc. format. So when you hear electron configuration, it means write out this sentence. All right, let's do it. We have the field order, and therefore we can start to populate it. We know that we have 6 electrons from carbon that we must populate. So when we write out the electron configuration of carbon, we must account for 6 electrons, starting at the 1s level. So let's write it. We have 1s, 2, and we know that's correct because the s can only contain 2 electrons. That's followed by 2s, completely full or filled with 2 electrons. And according to the order of filling, next we have the 2p. However, we only need 2 more electrons in the p orbital to account for carbon. Therefore, it's 2p2. So, we have 6 electrons according to the atomic number. We have 1, which gives us the period that we start in. Electron configuration must always start at the 1 and work its way through to 7. So we start the 1s, the s because that's the orbital type, and we see the filling. Then we have the 2, which means we have 2 electrons in there. Then we have the 2s2, 2p2, that's the number of electrons. And when we sum them, it equals 6. And we read it as 1s2, 2s2, 2p2. That's how we know we have carbon, because that is its unique electron configuration. Its electron configuration is 1s2, 2s2, 2p6. Now, some professors will teach you electron configuration first and then teach you the electron orbital diagram drawing later. I am going to teach you both as we go. Okay, so be aware of that. And I do that because I think as you catch electron configuration, it tends to be intuitive how to plug them into the diagram. The diagram is only how we represent where we place the electrons. So you write out the sentence and then you place the electrons in their proper place on the shelf. Got it? That's all the diagram does. It takes those electrons in your sentence and places them properly on the shelf. So you think of write the sentence first, then place the electrons on the shelf. So the electron configuration is writing the sentence. Now let's use the sentence to help guide us toward the orbital diagram. Orbital diagrams are pictorials of the electron configuration, showing the individual orbitals and the pairing of electrons, where they are on the shelf. Okay? The diagram explains how electrons are arranged within the atom. It shows the order in which the electrons are placed in the orbitals. And it's done by using boxes, lines, or bubbles to represent the orbitals. Okay? So we have carbon 6, 6 electrons. Its electron configuration, which you know how to write now, 1s2, 2s2, 2p2. And now we're going to simply create boxes, areas, shells, levels, sublevels to populate carbon with its 6 electrons. The first one's the S, the second one's the S, and then the third one's the P. So we have a 1s, a 2s, and a 2p. Note when we draw out the orbital diagram, we do not add the superscripts. Okay, so be aware of that. However, for instructional purposes, on the bottom of this slide, in the blue, shown on my slides, I've added them so you can see how it matches up. So, what do? An S orbital will be either one line or one box. Regardless of 1, 2, 3, 4, 5, 6, 7 S, an S is always one box. A P will be 3 boxes, 3 lines, 3 ovals. A D will be 5 boxes, 5 lines, or 5 ovals. And F will be 7 of those. So, since we have S and P, we have the 1s, which is one box with 2 electrons. Spin up, spin down, arrow up or arrow down. You can put double-headed arrows, it's okay. All right? And we say it's okay because of the habit of using double-headed arrows. Some will. But some of us prefer to be extremely picky about this, and we only use single-headed arrows. You will see in some of my presentations, I'll use both. Okay? But we have one arrow up, one down. In the 2s, we have arrow up, arrow down. That accounts for 4 electrons. In the P, and this is important to remember, we must populate each of the levels or each of the boxes first before we pair. So since we have 2 electrons, we go in the first box, the second box, and then the third one is open. It represents your X, Y, Z, or Z, Y, X. Okay? So we must remember to do that. Okay? We must pair only after we've filled all the boxes. The Pauli exclusion principles help us understand that, and Hund's rule help us to deal with it. Okay? So there we have it, the orbital diagram for carbon. Remember, orbitals can hold a maximum of 2 electrons and must have opposite spin, one up, one down. Within sublevels with multiple orbitals, Hund's rule states that 1 electron is placed in each orbital with parallel spins before pairing. Okay? Alright? So that's what Hund's rule helps us to understand, along with the Pauli exclusion principle. So Hund's rule helps us understand that we have to place 1 electron in each of the levels before pairing, and Pauli helps us to understand that it must be one up, one down. All right? So be aware of those 2 principles. Very important to orbital diagram filling. So that's how we do it. Electronic configuration, we write the sentence, and then we use that sentence to help design our orbital diagrams. So let's use some examples to reinforce what we know. And we're going to do this by showing you the electronic configuration, or the electron configuration, and the orbital diagram. Here we go. Let's take helium. If we look at the periodic table, we see helium with a 2. That means its atomic number 2, 2 protons, which also equals 2 electrons. Again, when we see the atomic number, for all practical purposes, when it comes to electron configuration and orbital diagrams, that's your electron count. That's how many electrons. So 2 electrons for helium. Well, since there's only 2, we can account for those 2 in the very first 1s. So we have a 1s2 for the electron configuration. The orbital diagram only requires 1 box because it only is an s orbital, 1 up, 1 spin down. Therefore, we have helium. Lithium. Atomic number 3. 3 electrons account for an electron configuration. So we'd have a 1s2, 2s1. That's it. We're done. Its orbital diagram then would have 2 separate s boxes. Not drawn together. Be sure it's clear that they're separated. Okay? So we'd have a 1s and a 2s to fill 3 electrons. So we'd have 1 up, 1 down in the 1s. Then we have 1 up in the 2s. Then we have beryllium. 1s2, 2s2 for the electron configuration. And then we have 1 up, 1 down in the s, 1 up, 1 down in the 2s. Note again that we do not write the superscripts above the notations in the orbital diagram. The superscripts are only written in the electron configuration, the sentence format. Okay, then we have boron. Boron's 5. And now we need a p orbital. But when we draw the p orbital, we must draw all 3 possibilities for the p orbital, even though we only need space for 1 electron. So in that case, we only put 1 electron on the shelf. Okay? So there you have it for how we draw some of these. And we use the field order to help guide us, since we haven't memorized it or we haven't learned yet how to read it from the periodic table. All right? Now, atoms with completely filled shells are called diamagnetic. That's a term you have to memorize and just know. Completely filled is diamagnetic because the magnetic field cancels each other out. Okay? If there's unfilled or unpaired, and you'll hear paramagnetic means unpaired electrons. Okay? That means it's not filled. If they're unpaired, that means it's not filled. Okay? When they're paired, that means it's filled. So if you have any unpaired electrons, any unfilled shells, energy levels, orbitals, then it's called paramagnetic. So diamagnetic, completely filled. Paramagnetic is filled. So if we look at helium, lithium, beryllium, and boron, we find that helium is diamagnetic, and lithium's paramagnetic, beryllium's diamagnetic, and paramagnetic is boron. Now, an interesting thing to note, hydrogen, which we don't show you here on the slides, but hydrogen only has one electron. That means the hydrogen atom, the monoatomic hydrogen atom, only has one electron. You would be tempted to refer to hydrogen as being paramagnetic. However, hydrogen in its most stable elemental state is as a diatomic. It is H2. Therefore, it is diamagnetic. It is a diatomic. You get it now? A diatomic element in its elemental state. So is oxygen, nitrogen, and all of group 17. They are all diatomic because they exist in their elemental state as dimers. They don't have an unpaired electron in their elemental state. So that's how we write the electron configuration, which is the sentence format. And this is how we draw the orbital diagrams, which are the boxes that we fill with arrows up, arrow down. Let's show some other examples and introduce the concept of valence electrons. Valence electrons. These are the electrons in the outer shell, the highest end, that participate in bonding in what you will learn later to be known as Lewis structures. So your valence electrons, you simply count all the electrons in the highest orbital. Okay, whatever the highest orbital in value is, count those electrons, and that will equal your valence electrons. It will also equal the electrons available for drawing Lewis structures, which you will learn later. Okay? So let's use some examples to introduce the concept of valence electron. Start with oxygen. And we're going to talk about oxygen in its atomic state just to illustrate our principle. But I need you to keep in mind that oxygen and fluorine, both shown here, are actually diatomic. They will not stay in this state in their elemental form. But to illustrate the principles, I want to use them. Okay? So, oxygen. The electron count on oxygen is 8 because its atomic number is 8. Therefore, I write an electron configuration according to the field order or based on my knowledge of the periodic table. I write 1s2, 2s2, 2p4. That accounts for 8 electrons because the superscripts add up to 8. 2 plus 2 plus 4 equals 8. I can now draw the orbital diagram. 1 up, 1 down in the 1s, 1 up, 1 down in the 2s. Now I have to draw the p orbitals, and I have to draw 3 boxes for the p orbital. So for the p orbital, remember, I have to fill across before I double up. So in the case of the p orbital, I went 1 up, in the first box, one up in the second, one up in the third, and then I came back to the first box and did one down. Okay? Next, take a look at fluorine. Again, fluorine is actually diatomic in its elemental state, but in its atomic form, it is paramagnetic, as is oxygen, only in its atomic state. So, the electron configuration for fluorine is 1s2, 2s2, 2p5. Its orbital diagram has one up, one down in the 1s, one up, one down in the 2s, one up, one up, one up, one down in the 2p. And that's what its orbital diagram would look like with an unpaired electron, which we would name as paramagnetic. And then we have neon. Neon has 10 electrons that we have to count for. This electron configuration is 1s2, 2s2, 2p6. The orbital diagram has the 1s field, 2s field, and all of the 2p field. And if you will watch me write it, I would write all of them with the spin up first and then come back pairing down. It is diamagnetic because it does not have any unpaired electrons. All the electrons are happily filled. This is a noble gas. Noble gases will be diatomic. They're perfectly filled. Now, when we look at the valence electrons, if we look at the valence electrons in oxygen, and when we talk about drawing oxygen as an atomic species, we only draw it as the monoatomic oxygen. So we have our monoatomic oxygen here, and if we look at the highest N value, that N value is 2p. Okay? So the highest value is 2, and the electrons at that highest value are residing in the S and the P. So we total the number of electrons of 2 in the 2s and 4 in the 2p to give us the valence electron count for oxygen at 6. Okay? So we look at the 2, the highest N value, and we sum them. That's straightforward. If we look at fluorine, monoatomic fluorine, we have 2 in the 2s and we have 5 in the 2p for a total of 7 for its valence electrons. That's what we do. Now we can do that by looking at the diagram, or we can look at the electron configuration. If we look at the electron configuration, we add the superscripts with the highest value, N value. And we note there's 2s2, 2p5, 5 plus 2 gives me 7. Likewise, or in a similar fashion, we do for neon, and we look at the 2 level, and there are 8 total electrons. 8 electrons fulfills what's known as the octet rule, which is why neon and the noble gases are so stable. They're so stable because they have 8 electrons in its valence shell. Now, remember, valence electrons participate in bonding. Since the noble gases, like neon, already have 8, they do not participate in bonding. Fluorine and oxygen, on the other hand, do not have 8 in its valence electron structure. Therefore, it will participate in bonding. And note again that group 17 form diatomics, which allow them to be diamagnetic and fulfill the rule of 8, the octet rule, around both atoms. Let's look at some more examples. Helium, lithium, beryllium, boron. We've already written the electronic configuration for these, and we've already drawn the orbital diagrams for these. So we simply take a look at them and count, and we know the helium, which is a noble gas, has 2 electrons is perfectly happy. It doesn't fulfill the rule of 8, but it is diatomic and has already satisfied its thirst for electron balance. And it is part of the noble gas family that does not participate in bonding. It does not participate in bonding. Lithium, we do the electron configuration, 1s2, 2s1. We can draw the orbital diagram, and we can count our valence electrons from either process. And we get 1 valence electron for lithium. Beryllium has 2 valence electrons. It's diatomic. It is 1s2, 2s2 in the orbital diagram. Spin up, spin down in the 1s, spin up, spin down in the 2s. 2 is the highest in value, therefore 2 valence electrons. For boron, we have 5 electrons to account for, 1s2, 2s2, 2p1. We write the electron configuration or the sentence format according to the field level. And then we draw out the orbital diagrams, noting that since we have a p orbital, we must draw all 3 shells. It is unpaired electron, therefore it is paramagnetic. The highest in value is 2. So we have 2 in the 2s and 1 in the 2p. We add them together and we get 3 valence electrons. And that is how you account the valence electrons. By looking at the electron configuration, we add the superscripts with the highest values. That's our valence electron count. Note that that valence electron count will not exceed 8 electrons. Okay? We can also count the number of arrows up and down in the highest in value, looking at the orbital diagram, and we will get the exact same number. Now, chemists have also developed a way of writing a shorthand notation of the electron configuration. That is, for writing the sentence format of the electron configuration of elements and atoms. We call that the core or noble gas format. The core method is a shorthand notation that credits the first portion of the electron configuration to the preceding noble gas as its core, as the core of that atom. And we will show you exactly what that means in some examples. We show you here the periodic table. The core values are those to the far right, the noble gases, which means that, for example, helium. Hydrogen is the only atom we have before helium. Therefore, hydrogen does not have a core. However, if we move to lithium or beryllium, lithium and beryllium come after helium. Therefore, the core for lithium and beryllium would be helium. And for anything else in period 2, up to neon. The core for sodium, magnesium, aluminum, silicon then would be neon. So you look at your position on the periodic table and you look back to see what its core structure is, its core notation. And we write that notation with the element in the center and brackets on the outside. So let's use this to describe the electron configuration of some elements. We will use, for example, boron, sulfur, and calcium. Boron has 5 electrons. We know that because of its atomic number. We write the electron configuration as 1s2, 2s2, 2p1. If we look at where boron is located on the periodic table, we see that it comes after the helium core. So we can abbreviate then all the electrons up and including helium as helium. So we would write helium, and then we would continue to write the independent notations as 2s2, 2p1. In the case of sulfur, we have 16 electrons. Therefore, we must account for 16 electrons in its electron configuration. And we'll account for those electrons by writing 1s2, 2s2, 2p6, 3s2, 3p4. Now, it's important that you count the electrons and add them to be sure that you haven't made a mistake in your count. That is another common mistake that's made, that sometimes in haste, students and professors alike will write a number that's not true, not because you don't know it, but simply because you got a little sloppy or got a little careless. So make sure you resum the total subscripts and make sure it matches the value of 16. And in this case, we have 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 4 is 16. So we have the proper electron configuration for sulfur. To write its core, we note that sulfur is after neon. Therefore, the core for sulfur is neon. And then we continue to write the individuals as 3s2. And if we look at the periodic table and move across, we see 1, 2, 3, 4 in the p area. Okay? Now, I'd like to show you, using sulfur again, how we use the periodic table to do this notation. I'd like to show you by starting at the far left with hydrogen. We note that sulfur is a 1s2. Therefore, hydrogen is 1s1, helium is 1s2. We continue next to lithium, which is 2s1, beryllium 2s2. It's done. Now we skip across the valley, across the D's to B, boron, and we continue naming it as 2p1, 2p2, 2p3, 2p4, 2p5, 2p6 ends at neon, which is the core. We continue next down at 3s1, 3s2 is at magnesium. We skip across the valley to aluminum, which is now 3p1, 3p2 for silicon, 3p3 phosphorus, and 3p4 sulfur. So you can simply count down the periodic table and note which block you're in to determine your electron configuration. That is also how you will always know the order when you have a periodic table available. Okay? So let me finish this discussion by using calcium as an example. Calcium, we have to count for 20 electrons. So we have 1s2, 2s2, 2p6, which gets 10. Then we have 3s2, 3p6, 4s2, which gives us a total of 20. The core for calcium is argon, because argon is behind the calcium, or you pass argon to get to calcium. And we write the argon notation in brackets. Then we write 4s2 for its shorthand or its core notation for the electron configuration. So if you're asked to write the core, then you would write the noble gas followed by the remainder of the notation. Now, if on an exam, at least for my lectures, I don't indicate core, the expectation is that you will write the entire electron configuration. For me, I will ask for the core, but the default position is to write the entire electron configuration starting with 1s2. We've also noted for you the number of electrons in the core value noble gases as well. So just to complete this section, we point out the number of valence electrons and whether it's paramagnetic or diamagnetic. In the case of boron, the highest occupied, the highest number for electrons is 2, and there are 3, so we have 3 valence electrons. One is unpaired. We see that in the p orbital, therefore it's paramagnetic. In the case of sulfur, we note that the highest value, N value, is 3, and we have 6 electrons there. We know that a complete p orbital would contain 6 electrons, so it's paramagnetic, but the total electrons for the valence electrons is 6 for sulfur. And then for calcium, we have 2 valence electrons, and we know that a completely filled s orbital contains 2 electrons, therefore everything's paired, therefore it's diamagnetic. To determine whether it's paramagnetic or diamagnetic, simply look at the last orbital and ask yourself, is it filled or unfilled? If it's filled, it's diamagnetic. If it's unfilled, it's paramagnetic. So here we show you another example of how to look at the core abbreviation. We have sodium here, and so its core would be through neon. Then we have the electrons after neon. In this case, they are the valence electrons. So in sodium, we would have 1 valence electron, and that would be the same for all of group 1. Then we show you another example of group 2. Just so you'll have a reference point of what it looks like to do these in group 2. So you have group 1 and group 2 compared there as a reference point. And you note that the number of valence electrons changes as we go from left to right on the periodic table. More valence electrons in elements to the right than to the left. But then there are some exceptions on the periodic table. We show you one exception here. We show you the exception of copper 29, which is a transition species, a transition element. That transition element should end with 3d9. However, because of the proximity and the closeness in energy of the 4s and the 3d for copper, it actually repopulates or promotes one of the electrons from the s to the d, and this is what its electron configuration would look like. So let's take a look at electron configuration when we move to transition elements. That means they're D block of elements on the periodic table. The D block elements are those located in the valley. Alright, so let's look at it. When we have a D block or a D transition element, it's important to note that when we reach the D block, we reach that at period 4. When we reach period 4, the D block is period 4 minus 1, which means 3D. So the earliest D group that we encounter is a 3D. It is named 3D because of the energetics associated with that set of atoms and elements. Okay? So you want to note that as we do the electron configuration. Otherwise, it's the same. This is why it's also important to use your periodic table as you think about these. So let's use manganese. Manganese has 25 electrons. Its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and now we entered the D block, 3d5. Manganese is located at 3d5. If you look at the D block, we start with scantium. 1, 2, 3, 4, 5 atoms, elements over. We're at manganese, so it's 3d5. If we use the shorthand core method, then we look back from manganese and our core becomes argon because it is a noble gas with 18 electrons, we might note, in it. So we pass argon on to 4s2, 3d5. Let's look at germanium. Germanium has 32 electrons. So if we do the electron configuration, we know we start the 1s2 and we proceed to 4s2. We drop down to 3d and we completely fill all the d spaces, which are 5. We have 5 shells available in the d, therefore 5 spaces, 5 degenerate levels. Therefore, we fill them with 10 electrons because 5 times 2 gives us a total number of electrons to fill that set of electron shells. And then we move on to the 4p. 4p1, 4p2 at germanium. So that's what the electron configuration for germanium would look like. It's important to remember when we reach the fourth period, fourth row down on the periodic table, we find that we are at the 3d. It's n minus 1 for that d level. We can also draw out the electron orbital diagram for the d transition elements, and it would be as shown here. You now know how to draw up to the 4s. After the 4s, we create 5 different shells, degenerate shells, same energy shells, to populate 5 electrons. Now, as with the p, once we draw 1d, we must draw out all 5, even if they are empty. Okay? So that would be for manganese, as shown here. We will talk about valence electrons for transition elements in future discussions. Germanium, we will write out its electron configuration. We could draw the electron orbital diagram, and in fact, you can draw the diagram without writing the electron configuration. However, we would like for you to label each of the shells, each of the sublevels for the atom. And so as we label up the germanium, we come through the 3d, which is after 4s because of its energetics on the periodic table. We fill the entire 3d with 10 electrons, and then we move into the 4p, which has 3 degenerate shells that are available for populating with electrons. We only need to populate 2 of those. However, we notice that it is unpaired. Therefore, it is paramagnetic. But it has a total of 4 valence electrons. You might recall that carbon also had 4 valence electrons. As a matter of fact, any atom in group 14 will have 4 valence electrons. Any atom element in group 15 will have 5 valence electrons. Any element or atom in group 16 has 6, group 17, 7, group 18, 8, group 13, 3, group 2, 2, group 1, 1. That is how the electrons are populated on the periodic table. According to their groups, they each have a unique set of valence electrons. However, any atom or element in that group has the same number of valence electrons. There's an exception to the electron configuration in the transition elements in chromium. We show you this exception in chromium, which has 24 electrons, and it should be a 3d4, but in fact it is a 3d5 because an electron from the 4s2 is repopulated because of these levels being degenerate, these levels being at the same energy level, and there are some other elements like that on the periodic table. So just be aware there are some exceptions. If for some reason on an exam in my lectures you encounter an exception and you don't write it properly, occasionally, depending on the nature of the problem, you might receive the points. But be aware there are at least two exceptions that we have pointed out to you in this lecture, chromium and copper, and we expect you to be familiar with chromium and copper as being exceptions to the population rule. Let's take a look now at the F transition elements. In the case of the F transition elements, once you reach a period, it's that period minus 2. Okay? So if you're at period number 6, the F population would start at 4. Okay? And in fact, 4F is the earliest F populated orbitals available. Okay? So let's just take a look at cerium as an example. Cerium has 58 electrons. Therefore, we write out the electron configuration for it. And we find that we move through the 3d10 back to the 4p2. Then we complete the 4d10 back to the 5p6, 6s2, and then we drop down to the 4f2. It's on row 6, period 6. Therefore, F is in minus 2 for 4F and populated with 2 electrons. If we write the shorthand notation, we note that its core is at xenon. And after its core at xenon, we have 6s2, 4f2. We could write out the entire electron orbital diagram here for sake of space and the ability to look at it on the PowerPoint. We started at the 6s. You know what happens before that. You know how to write all of those. We start at 6s, and we know that there are 2 unpaired electrons in the 4f, but we have to write out all of the f, which means there's 7 shells, degenerate shells, same energy shells available for the f, populated with 2, both with spin up. So we practice how to write electron configuration. We've practiced how to write or how to draw electron orbital diagrams. We know how to count the valence electrons by counting all the electrons in the highest n value. And we know that that number of electrons can range from 1 to 8. We also know how to recognize whether it's paramagnetic or diamagnetic. Diamagnetic means that everything's paired, no unpaired electrons. We know that if they're completely paired, it's diamagnetic. Again, if it's unpaired, meaning it's not completely filled, then it's paramagnetic. We know how to do that. We know where to get the electron count from the periodic table. Its atomic number. And we know how to adjust our field order once we reach the D, which is n minus 1, or the F, which is n minus 2 for the number of electrons. This table then summarizes some examples for you to look at to help you know how to do these. And we also note the core notation of it. And it's important to remember that in my lectures, the expectation that you write the entire electron configuration unless I mention or say that you can write the core. Thus far, we've talked about writing electron configuration for neutral atoms, neutral elements. We can also write electron configuration for ions, and we can also draw the corresponding orbital diagrams. A cation, positive charge ion, forms when one or more electrons are removed from an atom, when it is oxidized. For main group elements, the electrons that were added last are the first electrons removed. So, you would write out the normal electron configuration for sodium, for example, and then if it's oxidized by one electron or it loses one electron, you simply remove that one electron from the highest orbital. In the case of sodium, that would be the 3s1, which would go to 0, which means you don't write that for sodium plus. Another example for aluminum. Aluminum would end with a 3p1. For losing 2 electrons from aluminum for an oxidation state of +2, we would remove 1 electron from the 3p and 1 electron from the 3s to give you the aluminum +2 ion. Note that for transition metals and intertransition metals, the highest Ns electrons are lost first, and then we follow N-1d or N-2f electrons are removed. An anion, a negative charge ion, forms when one or more electrons are added to the parent atom when it undergoes reduction. The electrons are added in the order predicted by the Aufbau principle, meaning the field order based upon its position on the periodic table. In the case of phosphorus, we would have a 1s2, 2s2, 2p6, 3s2, then 3p3. If phosphorus gains 3 electrons, it becomes a p-3, then we fill the rest of the p orbital, the 3p, with 3 electrons, paired according to Hund's rule. And remember, when we fill the shells, we follow, again, Pauli's principle. We know we have to have spin up, spin down, and we have to add 1 electron to the degenerate levels before we pair them. So follow those rules, and therefore we will have the reduced form of phosphorus. There is another principle that's important to note, and you will want to pay attention to this principle and practice it. Atoms and ions that have the same electron configuration are said to be isoelectronic. In other words, an atom, an element, an ion, cation or anion, is isoelectronic with whatever element has its same electron count. Now, the atom itself that has an isoelectronic configuration is not a new element. It is, in fact, the same element. However, its electron count is the same as some other element on the periodic table. We show you some examples of isoelectronic species. N-3, O-2, F-, Ne, sodium plus, magnesium +2, and aluminum +3 all have the exact same electron configuration, although they are identified by their own unique atomic number, which is equal to the number of protons. This is why we take caution in assigning the number of electrons as being always equal to the atomic number. It is only equal to the atomic number when the atom is neutral. Likewise, for P-3, sulfur -3, chloride -3, and so on and so forth, they all have the exact same electron configuration, although their atomic numbers are different, meaning the number of protons are different, but the number of electrons are the same. So, elements and ions that have the same number of electrons are said to be isoelectronic. And that is a critical principle to understand about electron configuration, particularly when it comes to ions. So, an example might be where you had an ion and you wrote the electronic configuration. Your professor might ask you what element on the periodic table is that ion isoelectronic with. You would then count the number of electrons and then use that number of electrons to match against the atomic number on the periodic table. And your ion would be isoelectronic with that element. It is not that element, but it has the same electron configuration with that element. One of the results of the atomic structure of elements and atoms is that atomic structure affects its covalent radii. Recall we said that valence electrons participate in bonding. Each atom on the periodic table has what's called a covalent radii. What's that? It has a distance that it uses to form bonds with other species or with itself. Covalent radii is that distance between one element's center to another element's center to form a bond. So it's a covalent radii. So the covalent radii is defined as 1/2 the distance between nuclei of two identical atoms when they are joined by a covalent bond. Defined as 1/2 the distance between the nuclei. So be aware of that. You know what a radius is, or radii in geometry, it is the same thing. Down a group, and this is what you want to remember. These principles are important to memorize. You will, in most freshman chemistry classes, be tested on these principles. Down a group, the principal quantum number n increases, 1 through 7. Okay? You want to be aware of that. So, the principal quantum number n increases by 1 for each element. So, if you know the element and you go down, it goes 1, you count 1, 2, 3, 4, 5, 6, 7. That's all we're saying. The electrons are added to a region of space that is increasing further from the nucleus. As a result of this, the size of the atom and its covalent radii, or radius, increases down a group. That's the bottom line. The size of the atom and its covalent radius increases down a group. So as you go down, the atom gets bigger. Kind of makes sense. More rings, it gets bigger, which means its covalent radius gets larger. That's important to note. So atoms get larger going from top to bottom. That's the bottom line of what we're saying here. Okay? Atoms get larger going from top to bottom, which means the radius of the atom gets larger going from top to bottom. Ionic radius is the measure used to describe the size of the ion, defined as 1/2 the distance between the nuclei. Not much difference in understanding what a radius is. Okay? A cation is always smaller than the atom from which it is derived. So if you make a cation, it is smaller because it loses electrons. You lose electrons, it gets smaller. You gain electrons, it gets larger. That is what these two statements are made. So an anion is always larger than the atom from which it was derived. Also note, the greater the nuclear charge, the smaller the radius is in a series of isoelectronic ions and atoms. Okay? So to understand this, or really to grasp this, you want to think about when you add electrons, things get larger. When you remove electrons, things get smaller. Okay? So notice what happened with aluminum. Has a value of 118 and it goes to 68 when it goes to the cation. That's because it lost electrons. Electrons, as you know, when it comes to protons, neutrons, and electrons contribute to size. Protons and neutrons contribute to mass. Sulfur starts with a 104. Add electrons, 2 electrons added. It undergoes a reduction. That is, reduction as in a chemical reduction, as in redox, oxidation reduction. However, its size gets larger. So, when an element or an atom undergoes oxidation, it gets smaller. When it undergoes reduction, it gets larger. Those are the two principles you want to hang on to. Other important principle that comes out of understandings about atomic theory, quantum mechanics, is the following. The amount of energy required to remove the most loosely bound electron from a gaseous state in its ground state is called its first ionization potential. Really deep term, right? The first time it ionizes is called its first ionization potential. If it does it again, it's called its second ionization potential. If it does it again, it's called its third ionization potential. So you can count the number of electrons in the equation to determine how many ionizations it underwent. Which ionization was finally used as first, second, or third. You want to retain that principle. Another principle about variation in ionization energy is the following. Energy is always required to remove electrons from atoms or ions. So ionization processes are endothermic. That is a critical part of this discussion to remember. They are endothermic processes. That is a critical note to have and remember. Okay? And the IE values are always positive. Energy is always required to remove electrons. Therefore, it's endothermic because it needs to absorb the energy. And the IE values are always positive. So remember that. Something else to note. As size, atomic radius, increases, the ionization energy decreases. In other words, it's easier to remove an electron from the outer area than from the area closest to the nucleus. The closer you get to the nucleus, the harder it is to remove that electron. So as size, atomic radius, increases, ionization energy decreases. So you can remove an electron from something that's in group 7, not group 7, in period 7, row 7, than you can from something in period 1 or 2. So ionization energies decrease down a group, increase across a period. Okay? It increases across the period, meaning from left to right, and it decreases down the group from top to bottom. There are some variations in this trend, however, but in general, this is what we would expect you to know about this area of energetics related to ionization potential. And what about electron affinity? The electron affinity is the energy change for the process of adding an electron to a gaseous atom or its form. In other words, what is its affinity for doing this? So, that's what the electron affinity is. It is the energy change for the process of adding an electron to a gaseous atom. All right? So you want to know that definition of electron affinity. And we show you a diagram here. We have X plus an electron, and we get X minus in the gaseous state because the electron is added, and there is an electron affinity energy value associated with that process. This process can either be endothermic or exothermic dependent on the element. For some elements, energy is released when the gaseous atom accepts an electron. Therefore, we get a negative EA, which is exothermic. For an element of energy required for the gas atom to accept an electron, it is positive and is therefore endothermic. In other words, the basic definitions of endothermic and exothermic apply here. Energy on the right side of the equation is exothermic, on the left side is endothermic. Negative is exothermic, meaning it's released. Positive is endothermic, meaning it is absorbed. And then we give you some reference tables here to take a look at. This is just for you to be aware of. And then we also give you an electron affinity value table. Be aware of it. It comes in handy if you have to do calculations related to electron affinity. And there you have it. That completes Chapter 6, Lecture 2. Lecture 2 of Chapter 6. electronic structures, and periodic principles of elements.